Hi, I'm Eric Grolke, and I'm the instructor for Process Design 455 for the fall of 2017. What we're going to do today is talk about workflows for process design. In particular, I want to show you the kind of workflow you'll be doing on the problems that we will assign you in this course. It's going to be important for you to see what kind of things you need to do, and then as you're working in teams, put the team efforts to accomplishing each one of the workflows and then integrating them for the final report. The way this course is going to be graded is we are going to have a report that you're going to deliver. We will grade the grammar, the writing, the organization of the report. We will grade the technical solution. And that would be your assumptions, the process design, what you have done with the physical chemical properties, the final results, material and energy balances, cost, etc. We're also going to grade separately the economics. And in general, when we optimize something, it's going to be optimized with respect to economics. There's also one other category that we take very seriously, which is other factors. And I will explain what that means, but it has to do with, is there a market for what you're making? How easy or how hard will it be to operate your process? Is there any intellectual property associated with it? Do you match and integrate with existing or future regulations for this area, this technology area? And then finally, can you scale the process up and down based on capacity changes in the marketplace? So we're going to talk about these four elements for the first problem, which is a toll processing problem associated with taking a stream, making two different products. One is sent back to a process, the other one is sent to wastewater. And we're going to go through each one of these four elements and talk about what you might put in the report. So the feed is going to come into this process, and what this feed happens to be is very simple. We're going to have a 30% ethanol in water feed. It's going to come in at 250 pound moles per hour. And by the way, these are academic kinds of specifications. If we were actually doing this for a plant, we would have this probably in mass specification instead of pound moles. This is going to make it a little bit easier when you start your material balances. We're going to try to generate two streams. The first one we want to generate is the product one will be a stream which is 80% ethanol and water. And this will be sent back to the process. We'll put a recycle up here. And then we're going to have a waste stream. The client that has provided us our challenge has thinking that this waste stream might be 1% ethanol in water. And this might be sent then to wastewater treatment. Okay, so in doing process design, we're interested in certainly the technology here, but we have some other things that are important to us, we need to know what kind of energy streams we have. We may have other utilities that we need for this process. If we want to do economics, we also need to know capital costs. And then this is all going to be done in a context of other factors. That is, are there any, we talked about things like regulations. Are there any regulations on these streams? Maybe not so much this one, because this is going back to a process someplace. Its specifications are sent by the requirements for recycle. But this one, going to wastewater treatment, is of concern. It's got ethanol in it, and if you send it back to wastewater treatment, you're going to be paying a cost for the degradation of every pound of the ethanol. So that's going to be a question. The client has also specified a feed which happens to be subcooled. And I'll put a question mark there. So we've got two client specifications. 1% ethanol as a product, put a surprise there, and a subcooled feed, I'm going to put a surprise there, which may not be optimal for either the client or for us. So these are things we're going to come back and look at once we have gone through a complete exercise to do a cost. What I'm talking today about in terms of process workflows is we are going to be going through this process of workflow many times, or we should be going through this many cycles as we are improving our design. So what we're going to talk to you today about is getting to a first complete run on the report, technical solution, economics, and other factors, so we can then use that as the basis for improvement of our overall process. So that's what we're after today. We're after to show you methods to quickly get to an initial answer, which you will then improve by going through some cycles. Either you might change the report, you might change the solution, you might change your assumptions about economics, and other factors could come in and affect some of your assumptions with the process as well. So organizing all this into a good design report is a challenge for anybody. Well, let's start first of all with the process. We're going to do a very quick synthesis tree, and let me keep the color blue. So if we had a very complex process, we would be talking about what steps we need to go through. Maybe we have a reaction step, maybe we have some separation steps, maybe purification steps, maybe we have 2 or 3 other reactions before we get to a final product list. And so we would generate a synthesis tree in which we've integrated all the reactions and the separations we need to do to make a specific product. In this case, this is almost all separations. So if we looked at this very carefully, the first thing we'd do is say, gosh, the best choice I have for separation here is distillation. So my synthesis tree is pretty simple. I'm going to use distillation. I'm not going to use crystallization or some other separation technique. So that's pretty simple. The question is now, what equipment am I going to use to do the distillation? Well, I have three choices. One would be a batch column, and then I might have a continuous column. I might do the continuous column in two ways. I might have a tray column, or I might have a patch column. In general, if we're not doing specialty chemicals, or we don't have any unique specifications, we probably will not do a batch separation because it tends to have, because we're starting and stopping things, it tends to have startup and shutdown problems. Utilities are discontinuous, so you have to size the utilities for more than an average rate of delivery. You have to size it for when you are working, which will be at a faster rate than if you did a continuous process. The energy requirements during the time you are running the batch process will be higher than they would be for a continuous process as well. So because this is a very simple separation, we probably will not use batch. We probably will use tray or pack column. I would like you to size both of these for this problem because we need to decide which one of these might be better. There are operating challenges, there are cost differences, and it's a very simple problem to look at a few equipment changes to see what's going to happen to the overall cost. So let's talk about how we're going to do the technology, the technical process. I'm going to sketch a distillation column down here. Flow going in someplace, and since we don't know where it is, we'll go in the middle. We'll have a distillate coming out. We will have the bottoms coming out. What we're going to have you do, both at the top and the bottom of the column, is we're going to go into a little bit more detail. I'm going to blow this thing up to show the vapor coming off the top of the column. I'm going to send this into a condenser, and this will be a total condenser. We're not going to generate a gas stream. This is going to be a liquid stream. That's the first assumption. And this stream will also be a liquid stream. When I'm done with the condenser, I'm going to drop it down into a reflux drum. It's got some liquid in it. I'm going to put in a divider. And I'm going to send some of it as the product. And then I'm going to have some coming in as recut cycle to this column. So I want you to size the condenser, the reflux drum, and specify the divider. We're also interested a little bit in what we're going to do for control here. So I'm going to write that down. I'm not going to discuss that today. We'll just indicate that that has to be done. And we're going to probably need a pump in here someplace, but the pump is not going to cost very much money. Oops. Thank you. There we go. At the bottom of the column, we need a reboiler, and we probably will use a partial reboiler. So we're going to enlarge this section to show the liquid coming off the bottom, coming into a reboiler. And then I'm going to take the vapor off. This becomes the vapor feed to tray 1, or tray N, excuse me. In ChemCAD, trays go from 1 down to N. And then I will take off also the liquid And then this is the product. Product 2, which is this one. Okay, now, do I have enough to describe this process completely? And what we're going to do now is take 2 minutes and talk about battery limits of a process. And that is, what part of the plant are you going to assume is part of your project? Well, certainly we need the columns, we need the condenser, the partial reboiler, we need any pumps that are important, we need a reflux drum. If we decide to change this specification, right now the stream is coming in as subcooled, but if we decide to change that specification, we may need to put a heat exchanger of some sort in here. So I'm going to put that in as a question mark. That would be something we would add within our process if we decide we're going to change specs. The other thing we're going to need for this is we need to talk about storage, both for the feed and for the 2 product streams. So within our battery limits, we probably need storage. We need heat exchangers. We need our column. And we need a couple other vessels. And we need storage both for the feed and for the 2 products. So we're going to need to size storage, columns, heat exchangers, energy streams in and out. If we have a condenser, we'll need probably some cooling water. If we have a reboiler, we're going to need steam. We need to decide on the steam. And that summarizes the technology. So what we've drawn here then are the battery limits. It's called the battery limits. Of the process. Okay. And you have done all these things in various courses. You may not have integrated this quite as much as we're going to integrate for this problem, but you have done heat exchangers, you've done fluid flow, you've done distillation columns. So none of that is really new. What I'm going to do now is talk a little bit, I'm going to move from the technical solution workflow to the economics workflow. And to do that, I'm going to erase this board, and we'll start again on this side and talk about the economics workflow. Then we'll get to the other factors workflow. Okay, now we're ready to talk about economics. This is something you might have looked at a little bit, but in process design, we're going to spend a lot more attention to costs. A key reason is that we usually try to optimize a process with respect to its costs as we put it into production. This is not something we've talked a lot about in our other engineering classes, I'm sure. So let's talk about economics. And what I have for you is a template that we will follow in this class. We will use this template for all the problems. You will have to adjust it a little bit for each problem, but doing the same thing for 5 or 6 different projects will help you number one, understand how to do the economics better, and also think about how product to product or process to process the economics will change. So basically there are 6 panes or 6 frames in this template. And where this template starts off is with an economic analysis that's been used by Peters and Timmerhouse in their textbook for design. They have 160 pages on economics. It's very good. We will not repeat the 160 pages. We have put the 160 pages into the 6-frame template, just because it'll be easier for you to digest it, start to apply it, and then if you have a reason to go beyond that template, there's no problem. You can spend some time, think about it, and do that. So the first element in the template, the first pane, is going to be raw material and product costs. So what you're going to need to do for each one of your problems is to find out appropriate raw material and product costs for everything in the system. And this would include costs of waste streams as well. So you're going to have to be able to look at the literature. You also want to know ranges of prices. And it won't hurt, particularly in the more complex problems, you're going to be integrating the market with the process more than we're going to do here. And so you need to know something about market factors. Is this market growing? Is it changing? Do we expect the price of the raw materials to go up? Do we expect it to go down? What happens if it goes up and down? We can do that in the process. We can simulate the economics. We can also simulate the process to do that. The next piece that's critical is purchased equipment cost. So remember that we were talking about sizing the column, sizing a condenser, sizing a reboiler, sizing a reflux drum, sizing pumps, sizing storage tanks. All those elements are going to have a cost associated with them. There will be materials of construction that we have to consider which will impact the cost. So we need to put together a separate table for the equipment. In fact, this organization of raw material, purchase equipment, and the other four panes are things and tables that you can put directly into your report. So as you are doing these, you are generating report tables that will be included as you go through. And this is an important concept for this class, that is to be generating pieces of the report from day one of a given process. The next thing is to get to total capital investment. There are a number of factors that are important between purchase equipment costs and total capital investment. Once you buy the equipment, you're not done. You've got to install it. You've got, if you don't have a road to the plant, you've got to put in a road. You've got to put in other utilities. You have to put in entryways. You have to put in control systems, et cetera, et cetera. If you don't know anything else, you can approximate the total capital investment by taking the process equipment costs in dollars and multiplying by 5. For the chemical process industry, that is a typical factor that will get you from purchase equipment cost to total capital investment. So that's something if you don't know anything else. What we'd like to do then is to get to a total product cost. And what this does, the TPC, the total product cost, integrates operating costs. And there are a lot of their operating costs will include raw materials and product costs, but also another thing we haven't shown yet is utilities. One of the things you probably need to do is have a utilities table. So the total product cost integrates all of this stuff. This is plus infrastructure. into something like $1 per pound. Or maybe it's $1 per gallon. Or if it's the case of a product, it would be $1 per unit. Or euros per unit, something like that. This is important because we can then take the product cost, look at the market for that product and see, are we going to make or lose money by doing this? A very important question that you probably have not asked before in some engineering courses. Now that we have this, we need to do another piece, which is a cash flow analysis. So let me draw a cash flow plot that we are trying to generate from all this economic analysis here. So I'm going to put in some years. So here's years of the project, and let's just start here. 0. This is plus. This is minus. So during the first year, or before the first year that you're actually operating the plant, you will be investing in it. You will start to put in money. You'll build the plant, you'll buy equipment, you'll get it installed, you've got a workforce at the plant, and you won't make any money until you start operating the plant. The plant may not operate at 100% capacity at day one. And in fact, it may take you 3 to 6 months to get to full operating capacity of the plant. So for example, you might have a income. At this point, most of your outgo is not there except for the raw material costs and utilities. Those will sort of be constant. And you might start sloping up slowly, and then let's suppose you're at full production, then maybe it starts to slope up at a different rate. So it's not till year 2 or 3 that you recover the costs that you put into the plant initially. So this is the cash flow. This curve is cash flow. And it's basically income minus expenses, roughly. Although we'll get into more detail than that. A typical plant or process today, if we were doing just in a payback period, the payback period would be when this cash flow curve breaks 0. So this might be approximately the payback period. Of 2 years. Okay? So there's a number of tools that we can use to describe the value of a given investment. Each one is going to give you a slightly different answer. Your company will have its own way of looking at all these factors, and will have some ideas on how you would actually do this in that industry. So this varies by industry. We're just going to use this format and this workflow to help us go through and make sure we have addressed every issue that's major that we might need to address for our processes. So that's the workflow. We're going to do 6 templates: raw material and product costs, purchase equipment cost, total capital investment, total product cost, do a cash flow analysis, which is going to be put into a figure like this, these two will be slightly separate. So you'll generate a figure that shows the cash flow from your process that management would use to make a decision on whether you would build it or not build it. And so now we're ready to talk about the other factors. Okay, we've got a clean slate. We're going to go start with the other factors. What we're going to do with other factors is there are 5 key elements that apply to many technologies, not to all, and some technologies require more elements as these other factors. But I'd like you to generate an analysis of the 5 factors and then generate a radar plot, which is going to look like this. And the first factor we're going to consider is what's the market or the demand for the product. The second factor we're going to consider is operations or use. The third factor we're going to consider is IP, intellectual property. The fourth one is regulatory. And then the fifth one, which is almost always important, but we don't talk about very much, is scale up. Or scale down. And so what we will ask for in essentially every one of your reports is an analysis of each of these 5 elements for the process that you're designing right now. So let's talk a little bit about what would go in there for the ethanol water separation that we're doing, this very simple total processing. So what's the market in this case for the 2 products? So we are generating an 80% ethanol product. That's got a captive market for our client. And so they should be able to put a cost on it. There's another product, which is this wastewater stream. The client has not put a cost on that. And in fact, something we'll probably find out, I don't know all the answers because we haven't worked through the details yet, but we'll probably find out that a 1% ethanol waste stream is too high a spec, too loose a spec. In other words, it's going to cost us a lot of money to give somebody a 1% ethanol stream and make it disappear. We're going to want to do a better job in the distillation, which means we will go back and reset the specifications on the distillation column. So we will need to evaluate this one very, very carefully. And we will actually look at changing the design specs when we get through the cost. That's one of the reasons to get to a cost quickly. Based on a starting point for a process design, we have all these assumptions made. Some of them may not be very good. It's very helpful to go through a complete analysis, sort of a back-of-the-envelope analysis, quickly to find out, what do we do? What's the most important thing for us to do to improve this process? This is probably one of them. The next thing we're going to look at is operations or use. And we will ask ourselves some questions. Is it going to be hard to run this process? Is distillation difficult to do? And so this is basically relatively easy. We know a lot about ethanol water. We know a lot about distillation. We know a lot about heat transfer. And so, and operating this stuff might be pretty easy. So we ought to be able to do well in operations. This is not a concern for us. We might, just to start the radar plot, we might put operations, this is, if it's small, it's a problem. If it's large, it should not be a problem. So I'm going to put the operation out here. The market, I'm going to put right here. And because, number one, right now I don't have a value from the client for the return of the 80% ethanol, and we suspect that this is wastewater concentration is going to be a cost that we can't afford. We or the client cannot afford. So I think that's something that needs to be looked at. What about IP? Is there any intellectual property here? Well, distillation of ethanol water is quite common. Probably not much that we're going to get out of this. So, although we would love to have IP off of most any project, it's not going to be, it's almost a non-problem. So I'm going to put it out here, at least for now. The next thing is regulatory. And do we have some regulations? Yeah, we've got some regulations that we need to pay attention to. One is the spec on the out of the product, the P2 spec. Let me switch to a different color here. And we didn't talk very much about the products coming off, but we've got 80% ethanol. We're going to store it. So there may be a vent issue. Okay, if we're going to store it for any period of time, we have to choose a storage temperature and make sure we're not getting too much release to the atmosphere. Same for whatever we're going to do with this wastewater stream. It's going to be stored someplace. Do we need a special vent condenser on that storage to meet specs? And then finally, scale up. In this case, we've talked about two columns that we could choose. We're going to forget batch. We're going to do it continuously. And we're going to either do a tray column or we'll do a pack column. Now, we might tend to want to do a pack column because we know, gee, the packing is sort of cheap. All we need to do is buy the column shell. We throw the packing in, and it's Katie bar the door, no problems. However, if we have variable product flows to us, variable feed flows to us, we have to be concerned about scale up. How much variation do we expect in the flow rate as we are feeding this column? Or over time, how much variation do we expect in the flow rate as we are feeding the column? A tray column sometimes can be turned up and down by 30 to 50% in terms of the column feed and still generate a good product. The pack column usually is less flexible. That is, it's got a narrower operating range, and we need to be careful about what the total amount of material is that's coming to the process and how much we can scale up and scale down and still get good performance. So the scale up question, I've listed it as another factor, but what that marketplace is doing and how much we need are going to impact what we decide to make, because those two column types have different operating and scale up possibilities. So what I've done now is I've now completed looking at other factors. These are factors that you can apply to regulatory. Probably is a concern on this one. Scale up is also a concern. So our little chart looks like this. And so it helps us understand what we need to pay attention to. Well, we actually need to pay attention to a couple significant outside factors. What is the market doing in terms of prices, but also material coming to the process? Is this simple process that we've thought of, is that going to be fitting well with the current regulations? And finally, can we scale this stuff up and down in terms of process flow, depending on what the outside demand is? So this little other factors thing is really going to impact where we choose to spend time doing process optimization. It's silly to tune the process to a 1% ethanol bottoms product if that's going to be way too costly and might fail some regulatory operations, for example. So this simple example with your current problem is to show you how you might think about organizing the report, the technical solution, economics analysis, other factors, integrating those together in an improved process design, and finding a couple things that you can do different. What you've done when you've done this first pass is you've generated a base case. We're going to want you to generate the base case and then propose some process alternatives, cost them, and also look at the other factors as well to show that they have made an improvement, or maybe they have not made an improvement in the overall product. So this is a very quick view of what you'll be doing in each one of the problems assigned in 455. Thank you.